Firstly, we will begin with an important theoretical introduction in order to make it easier to understand this movie. Let us begin with the Slepian-Wolf principle, which talks about encoding of correlated sources. It is known that in order to encode a source X, a rate which is higher than the entropy of X is sufficient. This is a known consequence of the asymptotic equipartition property theorem, ape data compression. We will discuss the Slepian-Wolf theorem, which deals with the lossless compression of two or more correlated data streams. In the best known variation, each of the correlated streams is encoded separately, and the compressed data from all these encoders are jointly decoded by a single decoder, as shown in the following figure for two correlated streams. Such systems are said to employ Slepian-Wolf coding, which is a form of distributed source coding. Let us now consider the Slepian-Wolf coding theorem. The admissible rate region for the pair of transmission rates R1 and R2 of the sources X and Y respectively is the set of points that satisfy the following three inequalities. This admissible rate region is shown in the following figure. Pay attention to the two corner points of the rate region, numbered with 1 and 2. Now consider the following figure, which illustrates the case of the second corner point, where Y is transmitted first. Only the decoder has access to the side information sequence Y, which is correlated to X. In short, the Slepian-Wolf coding theorem says that the source sequence X can still be described with number of bits per sample, which equals to the conditional entropy of X given Y. In our simulations, we assume that the side information sequence Y is the output of a virtual binary symmetric channel with inversion probability of P per bit, while the input to the channel is the source information sequence X. We have used also random binning. The basic idea in random binning is to partition the space of Xn sequences into a number of bins equals to 2 raised to the power of the transmission rate R1 of each source distribution, also the space of Yn sequences. These bins will be built at random, hence they are called random bins. The set of sequences in Xn or in Yn that have the same index are said to form a bin. Thus, random binning's idea is similar to hash functions. Encoder chooses a large random index for each typical source sequence. It is known that a common performance measure of gossip algorithms is the time required to disseminate a single message to all the stations in the network. Thus, we have measured this time in our simulations. Moreover, a source sequence is chosen randomly for transmission. Then we produce linear equations on its bin index and transmit them randomly to the neighboring stations, which in their turn continue disseminating this information towards the rest of stations in the network. The method is more detailed later in the movie. Let us consider the following network, which implements a ladder graph simulation of our gossip protocol. This graph represents one of the versions of a network topology commonly known as the entity backbone, which belongs to the Tier 1 worldwide entity communications company and links Japan, the US, Europe, and Oceania together. Assume that there is one source of information. Assume also the source is the upper node at the left corner with the generator icon. Let us now run our simulation. Non-source nodes also join the flooding process. The alternating blue numbers above the nodes show the number of independent equations locally received in each node. We can see that there is a quick information dissemination process along the network. This comes from implementing network coding and is illustrated in having a fast increase in the number of nodes with non-zero independent equations. Despite the fast information dissemination process, there is a difference between the nearby nodes to the initial source and the distant nodes, which appears in the quantity of independent equations already collected in each node. This quantity is directly influenced by the node's topological placement. We assume that the correlation level between the initial source and each another node is constant, so that each non-source node requires the same number of independent equations. A node finishes its information collecting process and immediately begins decoding when its icon turns to be with a green lamp. Continuing to the decoding stage, it is obviously seen that nearby nodes to the initial source begin decoding the source information early before distant nodes. Let us stay with the animation. We have invested two encoding scenarios. In the first one, a non-source node which has finished collecting the needed independent equations will continue in producing linear equations which are built by linearly combining the equations it has. Or better yet, since it finished, it can decode and compute all the bits of the transmitted bin index and then send linear equations as if it was another source. Now we will compare between the results of the two scenarios. Let us consider the results graph of the first encoding scenario, showing us the needed rounds until finish collecting equations and begin decoding in each node. The only node which is directly connected to the initial source is the earliest decoding node. This is obviously due to its topological placement. In the other nodes, decoding begins to take place after around 10,500 rounds, with a growing time as nodes get more distant from the initial source. At the most distant nodes, those with high indices, the decoding process began after around 15,000 rounds. Hence, the difference in time of decoding between the nearby nodes and the distant nodes in this scenario is around 4,500 rounds. Let us now consider the results graph of the second encoding scenario, which also shows the needed rounds until begin decoding in each node. Here we can see that in the nearby nodes the decoding begins to take place after around 10,500 rounds, similar to the first scenario, and the decoding process in the distant nodes begins after around 12,500 rounds. Hence, the difference in time of decoding between the nearby and distant nodes in this scenario is about 2,000 rounds only. Based on the above comparison, we can conclude that the second encoding scenario is much better than the first one. In other words, combining directly on the bits of the transmitted bin index when producing a linear equation for transmission is much better than combining on a limited set of locally collected independent equations, even if this set is the complete needed set. This result is due to the fact that when using the second encoding scenario within intermediate nodes, then we can produce much more diverse set of equations in comparison with the first scenario, and ensures receiving of less dependent equations during the collecting period at each node in the network. Thus, nodes can reach faster to the decoding stage and send linear equations as if they were additional sources. This definitely helps and significantly increases the speed of information dissemination over all multi-hop networks. Next, we will present the coupons collector problem, which can be used to study a number of different communication problems. The coupons collector problem nicely captures, for example, the problem of content distribution over peer-to-peer networks, such as BitTorrent, where multiple copies of n file fragments exist within a network, and a copy of the file is acquired by collecting all these fragments, which are passed as messages over the discussed network. Let us explain how this relates to gossip. The bits of each message or fragment are the coupons, and instead of collecting coupons, network coding tells us it is better to collect linear equations on them. Look at the theoretical explanation in the final report which prove this claim. It is important to say that coupon collector applications are usually implemented by a gossip algorithm which works in a pool message exchange model. Look at the final report for more details. Here we have simulated the following star network, composed from 7 nodes collecting information, which are called also collectors, and one source of coupons in the middle. Let us consider the following result graph. It shows the sample size necessary for acquisition of the whole needed set of distinct coupons in each collector over only one run of the simulation program. For each collector there are displayed 2 columns. The left side one shows the quantity of the needed coupons, which has a constant value over the collectors, and the right side one shows the sample size needed for acquisition of 58 distinct coupons. Moreover, the following graph shows the average results over 5 runs of the simulation. We can see similar results to the first case. For conclusion, it is obvious that the sample size in the 2 cases has a little bit higher value than the quantity of needed coupons. Indeed, this satisfies the following theoretical inequality on the bounds of the average sample size, and when the field size equals 2, indicating to working with a binary field, we get that the average sample size should be with a value between r and 2r samples. This inequality is taken from the discussed theoretical material in the final report.